Okay, let's continue. Okay. So, a small recap before the break. What did we do? We used the whole concept of power to come to energy, and then by taking Newton, we integrate that, found the energy equation, and then we came with this nice energy equation that the kinetic energy plus the potential energy is constant. Of course, now what can you do with this? Well, it is a handy instrument because you use the equation of motion not as the equation itself, but in an integral form. So you can do calculations of systems where you are not really interested in what is happening between two moments in time, but you know that from one moment in time to the other moment in time, there should be conservation of energy. So irrespective of what happens in between, you can calculate at a certain event what is the state of the system. And as an example, I like to look at this case where you are the lord of the manor, and of course the manor is there's always an enemy, and as with Macbeth, the enemy is always in the woods, right here. They're hiding in the woods, and but you have a powerful cannon, and with this cannon you are able to try and get rid of your enemies. So you're able to fire a bullet with your cannon, this ball from your cannon with some muzzle velocity, which we call V0, that's the initial velocity. Of course you need sparks here to do that. And then, yeah, what happens? Well, I don't know, the ball flies in some direction, I don't know how, and then bang, it lands here on the enemy, who is hiding behind the trees. And of course, it's important to know the velocity by which you hit your enemy, because there is a minimal velocity. If it's too slow, then it won't work, then he will survive. So you need a minimal velocity. Let's assume there is no drag, so there is really, there's no air drag or no losses, so there's really energy conservation. So for this problem, we can easily say that the kinetic energy at this time plus the potential energy should be identical to the kinetic energy here and the potential energy here. Now let's assume that this is at a height h in relation to where you hit the ground. Then if we start in this configuration, then we can say, well, kinetic energy is apparently 1/2 m v0 squared plus, and the potential energy, if we take this as a zero potential, that's also all relative, but and then, yeah, is it minus mgh or plus mgh? Because you really get into trouble if you think, oh yeah, but by definition, the potential was minus F. Yeah, minus and minus is plus. Yeah, plus. So it's mgh. Yeah. And that also complies with our feeling, the higher you are, the more potential you have, right? So, and then on this side, the kinetic energy is of course 1/2 mv1 squared plus 0. And from this we are able to determine, of course, what the speed v1 is, the square root of v0 squared plus 2gh. So then we know how hard we hit the enemy. And it's interesting because we haven't solved the motion of the system, but we did solve the state after a while, at a certain event. Okay, so useful, but how is it helping us with the Lagrange equation? Well, let's go back to our system of bodies, our system of rigid bodies. And within our system of rigid bodies, we can immediately identify what the kinetic energy is. That's super simple. Remember, we had all these coordinates, x1 equals x1, y1, phi1, x2, y2, etc. until phi n, not n, phi b of the number of bodies. Oops, not nice. And so this runs from 1 to n, and the bodies is the number of bodies actually we have, b bodies. So these are the coordinates, and for the mass it's also super simple. We have this diagonal mass matrix, and so that's a diagonal, and on the diagonal we have all these terms, m1, m1, mass moment of inertia 1, m2, m2, etc. until ib, of the last body. Nice diagonal form. Then the kinetic energy in the system is given by T is 1/2 well, x dot I mij x dot j. Very simple bilinear expression of mass times speed. Now, how do we get back? Do you get back from this energy, from this T plus V is constant, to our equation of motion? How does our equation of motion look? Well, let's say sum of the forces is mass times acceleration. Now, the way from here to there was by integration, right? So the way from here to there is by differentiation. Yeah, but how are we going to how are we going to differentiate? Well, the integration, so in that route was we took the integral and then we did the quantity, the thing, times x dot dt. Or in other words, we take the integral times the dx. That was the way to get energy. So if you integrate with the x, you have to differentiate with the x, go the other way around. So we take this equation and then we take all these derivatives of these various coordinates, dxi is, well, 0 then, because it was constant and constant 0. Now, the second part is easy, so let's write that down. So that's just plus dv dxi, and of course everybody already recognizes, oh yeah, these are minus the applied forces, and that's perfect. And if we put that on the other side, you get the applied forces, so that works. But what is this term? So the d kinetic energy with respect to the coordinates. And actually I have no clue, because the kinetic energy is not a function of the coordinates. So what is going on? Well, remember, when we did the integration, we also changed our integration not to distance, but to speed. Yeah? So, and since the kinetic energy is a function of speed, we have to do the differentiation also in a little bit different manner. So we have to differentiate with respect to the speeds, but then we have to take the differential with respect to time to get rid of this time. Because then, if you multiply, if you look at this x dot times dt, and that's of course our dx. Yeah, so then we're again back in business, but because the kinetic energy is a function of time. So this is finally our way to get back to our equation of motion. And indeed, if you do this, you get nicely mij x double dot j, minus the forces, because that was by definition, the potential energy is 0. Or in other words, that's just Newton. So that's perfect. So now we know if we have the kinetic energy function and a potential energy function, then we can go back to our equation of motion by taking these differentials. And here the differential has to be a little bit different because of this change of parameters, or how do you say, boundaries. Okay. Until now, we only went up and down and up and down. It's like you go in an elevator and it's very interesting, but what does that bring us, right? We want to go somewhere else. So, and somewhere else we go by saying, well, now we have these coordinates xi, and we want to write them actually as functions of these generalized coordinates qj. And as a very simple example, in this double pendulum thing, and for instance we take these two angles, alpha and for instance here beta, and you want to write these center of mass positions, right, as a function of these two generalized coordinates. Well, that's actually super simple in this case. You can write x1 is L1 over 2 cosine alpha, and y1 is L1 over 2 sine alpha, and phi1 is alpha. Oh yeah, no, it's not so hard, right? And x2 is, then first I go to this point, and then I move up in that direction, right? So, L1 cosine alpha plus L2 over 2 times the cosine of alpha plus beta. And y2, well, that's identical, etc. So it's not so hard. That's the point I like to make. For this open loop system, it's pretty simple to write. Yeah?
Depends, however, on how you choose the second angle. No? Because in this case, you cannot...
Think of Shakespeare as you like it. It's all Shakespeare. As you like it, whatever. If you want to do the sum of angles, absolute angles, also good. Distances and angles, I'm okay with that. Length, also good. As you like it. As you like it. Okay. That should be it. Okay, but in general, so we're able to write xi is some xi of our generalized coordinates qj. And in our case here was I was 1 to I was 1, no, other way around. I was 1 to 6 and j was 1 to 2. Two generalized coordinates and 6 CM coordinates. Now the kinetic energy, remember, there was something with the speed, so we first have to define the speeds. Well, that is, again, super simple. X dot is xi, comma, j, nice comma, q dot j. So now we have the speeds. So writing the kinetic energy then is 1/2 times, let's start with the original, x dot I, mij, x dot j. And then we put in those velocities. So we get the xi, comma, k, q dot k, mij, and then we get the xj, l, q dot l. So again, you see, it is a thing, a quantity times these velocities. Or I can write, put all the Jacobian stuff together, mij, xj, comma l, this, and then here we get q dot k, q dot l. Or in other words, you could write, apparently there is some symbol here, m, k, l times q dot k, Q dot L. So we see that by means of these Jacobians, this one and this diagonal mass matrix is transformed in a more general mass matrix. And it's more compact, because when we start from 6 by 6, we shrink until a 2 by 2. So apparently there will be more entries and it will be compact. And it will also be configuration dependent. So note that this MKL is a function of our generalized coordinates suddenly. Whereas initially the mass matrix would be constant, but now it isn't. It will be configuration dependent. Okay, so that is the kinetic energy. Now the other part was the potential energy. Then the step we have to make is, oops, go back. We have to find a way to transform forces from the CM coordinates to forces in the generalized coordinates. So transform Fi's to, what are forces in the generalized? So these are forces at the CM, and then forces, at the generalized coordinates. But we haven't given them any name. We haven't introduced them. So I will give them a name, capital Q, J. And so there are apparently forces which go with that. So think of this double pendulum, where we took this angle alpha. Then apparently there's a torque here, M alpha. And then there's here some beta. And apparently there's here some torque M beta. Or think of the mechanism where you have this roller here, and then we had this distance S, remember? So that was also a generalized coordinate. Then the generalized force, so this is the Q, this is also a Q, Q2, Q1. Then this QI, well, I say I, QS, that's also good, is a linear force here, moving the thing back and forth. And why are they such? Well, because of energy, because we want that the following thing, so Q is actually defined by virtual power in the following manner, that the virtual power of that thing, that generalized force, should be this. Or for all generalized coordinates. So it's always the generalized force is always a force which goes in harmony with the generalized coordinate. Now, for simple things as relative displacements or rotations, it's easy to picture. But the moment you use as a generalized coordinate the sum of angles, then what does the force, the generalized force, how can you interpret that physically? Well, the only way to interpret that is from the equations. The same as with the Lagrangian multipliers. You also have trouble interpreting them, but you can do that easily by just writing down the static equations, assuming my Q is 1. How do the forces look like? Oh, then I identify that multiplier as a force in that joint, and the same holds for generalized force. Okay, so we have these generalized forces. Now, the relation between the generalized forces and the forces at the CM is, of course, super simple, because they should have identical virtual power. And so, if we have the virtual power of these applied forces, that is our Fi delta Q delta x dot I, and that should, of course, be identical to our Qj delta Q dot j. And we are able to write these as, of course, our xi comma j delta Q dot j, right, Fi. And of course, this should then hold for all virtual velocities, because we are now only working in that small set of generalized coordinates, and there are no constraints on those. And having in that, since this is now for all those virtual velocities Q dot j, we get j equations, or we get Fi xi comma j equals qj. Or in other words, we have found nicely how do these forces at the CM transform. Now the forces at the CM, so I'm going to rewrite them in the other order, is of course is, well, maybe, well, I'll put this Jacobian again for clarification. It's the same. Stop. No dot. No dot. It's of course the same as I wrote here, but it makes the argument a little bit more clear. Now what am I going to put in here is just the equations of motion as we have found from our Lagrangian method in the general CM form. So my generalized forces are apparently, and then I get this Jacobian, then I get Qj, and then for here I'm going to just write what we just derived, the Lagrange equation of motion, ddt times the kinetic energy with respect to our velocities. So, and then that's plus, sorry, not generalized. Not yet. This is what I want, but I don't have it yet. I still have these. The i's I have, xi's, and here the xi's. I want to get rid of all the x's. I want to write everything in terms of q or q dot. Now, if you look at the equations, you see that for one part that's super simple, because if you multiply this one with this one, then this x and this x disappears, and you just get partial derivative potential energy to the generalized function. So that is simple. But the other one is a bit more complex. So if you write that out, generalized forces is, let's do the first part, q x with respect to the generalized coordinates times this time derivative, kinetic energy with respect to the speeds. Now the other one, the multiplication, yeah, I will write it out, but you will see, oh yeah, those terms easily cancel. And then the final result for this one is just simply partial derivative of the kinetic energy, of the potential energy with respect to the generalized coordinates. And it's what you would expect. Because if you are a mouse who lives only in generalized coordinates, and you have to define in your mouse world your potential energy, then you would say, oh yes, I know, this mouse knows it. My dv dqi is minus qj. Right? And that's exactly what we have as a result. So that all complies. We're happy with that. Now this first part is a bit tricky, because I want to put this differential under within the differential sign here. So I'm going to do that. So I put dt. Then I have this differential here. Yeah. And then times this one. It's almost there. There's a dot here which is not there. So we are sort of in trouble there. But if I do this, yeah, then I do too much in the differentiation. So if I differentiate this, it's keep this constant times this differential plus this differential times keeps this constant. And that's what I'm doing too much. So I have to subtract that. Yeah, so I have to subtract, and now comes the iPad handy. I have to subtract here a term being minus, and what do I do too much? Well, I do this too much, the dt of this, dxi dqj times the dt dxi. That's what I do too much. And now it's all in order. So here we have qj. First of all, this one. I would like to get rid of this x dot, but here I have no x dots. Now, but if you look at the definition of speed, so x dot I is by definition dxi dqj q dot j, right? Now, if you do a partial derivative of the speeds with respect to the speeds of the generalized coordinates, then the answer is, well, exactly this guy. Yeah, because for every every time we have a q dot j, you have a component of this guy. So finally, the Jacobian of the coordinates is identical to the Jacobian of the speeds. And as you will do your homework, you will see that. So apparently what we are able to write here is, let's copy the whole thing. Copy. So apparently we can write here a dot and here also a dot. And with that we can just then strike out these ones and say, oh, that's easy. Then this term is going to be ddt of the kinetic energy partial to the velocities. Now the second term. What is the time derivative? This one. What is the time derivative of a Jacobian? Then again, we have to go back to our definition here. So the time derivative of the Jacobian is, well, the only thing we can find out what they are is by just looking at where does the Jacobian pop up, and the Jacobian pops up when we write the speeds, right? So we have the speeds here, qj, q dot j, we have a Jacobian. So if we take the time derivative of that, x double, then the time derivative of this one, then we get here the time derivative of this Jacobian, dt dxi dqj times q dot, plus of course the other terms. But this guy, of course, is a function of the coordinates itself. And as you know, taking time derivative, when it's a function, is the first partial derivative times derivative of. So taking the time derivative of these guys is identical to first taking the partial derivative, dq k, for instance, dxi, dqj, and then times the time derivative, q dot k. But note that this dxi, dqk, dqj is a symmetric thing. I mean, the order of differentiation doesn't really matter. I mean, they're identical. If you do that, then you can collapse the following things. So you can collapse, finally, this one is actually by definition is equal to the speed. That's x dot I. Or in other words, the time derivative of this Jacobian thing, time derivative of this Jacobian, is equal to the Jacobian of this time derivative thing. Yeah? So putting that then finally in our equation, where were we? So this was a, oops. Yeah. This was a dot, by the way. So here we can rewrite that as a dx dot I dqj times the dt dx dot I. And again, these go away, and we see the remaining term is that we have a kinetic energy with respect to coordinates. Now, combining everything finally, yeah, going through all this clutter, we finally come to the following conclusion. We take the time derivative of the kinetic energy with respect to the speeds minus the kinetic energy with respect to the coordinates plus the potential energy with respect to the coordinates. And this complies the Lagrange equation of motion in terms of generalized coordinates. Now, what does it differ with the one where you use center of mass coordinates? The only difference is this term. Yeah? And that's because these CM coordinates are a function in itself of these generalized coordinates. You can go through the derivation and you'll see it. Now, this formulating of the equation of motion and the solution for that is super simple for systems where you have only a few degrees of freedom. And as an example, I take a very stupid example, because in the CM coordinates it would also be a few coordinates, but it's to demonstrate the power of the method. And the power of the method, so the example is like this. I have a model of a harbor crane where the load is swinging. So you have these harbor cranes. How do they look? Something like this, and then here you have a ship, and you have containers on the ship, and here you have the quay, and here's the water, and all those ships. Here you have a crab, and you have to get a container and then move it. But we are now only interested in the swaying of that load, because if you move that load and you want to then put it here on an AGV, then you don't want the thing to swing too much. So I'm interested in a moving support where you have a load swing. So some of you may recognize this as a problem from another course. Anyway, we have a distance s here, and then here we model the container just by a simple point mass m at a distance l. There's gravity here. Well, what else do you need? Nothing. You have a point mass, that's the container, at a fixed length, and you just move the crab or the thing around, and then the thing will start swinging or whatever. And then you have gravity, and maybe everything will be jiffy. Now, to get the equation of motion with the Lagrangian method, what do you need? Well, you need two ingredients. Well, you need algebra. Remember Lagrange? You need algebra. So you need to be able to do this algebra, but that's easy. I mean, you can even ask a computer to do that. In a symbolic toolbox, it can do that. The only physical thing you have to do is define kinetic energy and potential energy for the system. Now, the CM coordinates are in this case just the x and y coordinate of this bulb, of this mass here. And the generalized coordinates, well, what do we take? Distance s, angle phi? Seems like a natural choice. You could also take other things, but for now let's do this. Meaning that the kinetic energy, I know, is very simple. That's always something like this: 1/2 m x dot squared plus y dot squared of this body B. And for the potential energy, that's mgh, so mg and then the height of the bulb. So there was mg and then the y coordinate of B. The only thing I now have to do is to define my coordinates in terms of the generalized coordinates, and the rest is algebra. Agree? Okay. Now that shouldn't be so hard. So the position of B is S plus L sine phi, right? Nice brackets. And the y coordinate is, there is no S, minus L cosine phi. Now, so potential energy is already defined. You just substitute that here, and that's in business. Then kinetic energy, we have to do one little thing more. We have to differentiate. So x dot b is s dot, and then the sine is cosine, so I get L plus L phi dot cosine phi, and y dot b is cosine is minus is L phi dot sine phi. Yep. Then we substitute that in the kinetic energy, so we get T equals 1/2 m times s dot plus L phi dot cosine phi squared plus L phi dot sine phi squared. And we can expand that, of course. We get s dot squared. We get plus 2L s dot phi dot cosine phi plus L squared phi dot squared. Something like that. Agree? And the potential energy is minus mgl cosine phi. So with these two things, and of course our beautiful formula, the equations of motion are, well, qj equals d dt of dt q dot j minus dt q and k plus dv. So just go through the motion, and I will make a little start now. We have some minutes. That's sort of. So what ingredients do I need? I need to do time derivative of the kinetic energy of first kinetic energy to speeds, and then time derivative, and then here kinetic energy only to coordinates, and this is also a simple one. So let's first do the dt ds dot. Well, what is the dt ds dot? That is m s dot. It's first part. And then here, oh nice, there's a 2 here and a half. They also go away. Wow. There's ml phi dot cosine phi. That's it. Then the second one to phi dot. Make the dot a bit more obvious. Well, then we have this part. Well, the 2 goes away. That's simple. And there's only one phi dot. That's also simple. So we get ml s dot cosine phi. And then this guy plus ml squared phi dot. Easy, eh? Easy peasy. Then the next step is, of course, that we have to take the time derivative of those quantities. Yeah, and that is ms double dot. Oh, I'm feeling good because mass times acceleration. I have a good feeling. Now, here I get more terms. Phi double dot cosine phi plus ml phi dot squared sine phi, and it's a minus, by the way. Yeah, and then the other one, phi dot. Yeah, again that guy, this guy, but now we get, yeah, what do we get? ml s double dot cosine phi, and then now this one is a minus, I'll do it good directly. S dot phi dot sine phi. And then this guy, that's easy. ml squared phi double dot. Those terms. And then we get the term dt ds is, well, if you look at the kinetic energy, there is no s in the there's only there's s dot and phi, but the distance s is not there. So the derivative is 0. And then the other one, the dt d phi, yeah, there we have a lot of numbers. So, oh, it's only this one. That's the only coordinate. So the 2 goes away. ml s dot phi dot, and then the cosine becomes a sine with a minus sign. So that's the minus ml s dot phi dot sine. Then finally we have to do the dv ds. Well, again, that was not in the potential energy. And the dv d phi is, yeah, that's there. Cosine is minus sine, so it becomes a plus again, mgl sine. When you then collect all the terms, you have to take this one plus this one. That's it, and this one, of course. And for the second equation, this one plus this one and this one. So that also fits on one sheet, I guess. So then the first equation is m s double dot plus ml cosine phi double dot minus ml phi dot squared sine phi. And then minus this term, so minus 0, plus this term, plus 0 is, yeah, the Q1. Q1, I would say, is the Fs, is this force which goes back and forth. In the second equation, now I'm going to reorder a little bit terms. I start with this one, and then I take this one. So I get, no, let's do it like this here. ML S double dot cosine phi plus ML squared phi double dot. And then minus ML S dot phi dot sine phi. And then minus this term, so that's plus ML. Oh, they are identical. Hey, they're the same. Did I make an error? They sort of cancel out apparently, these two. Okay. Plus, yeah, let's put that here. MGL sine phi is, well, let's call it M phi. And then finally we can write our answer as a nice mass matrix times acceleration is forces. And the accelerations are S double dot, phi double dot. Then the first term is of course an M. And then the second one is a ML cosine phi. And then on the right hand side I have to push all the other stuff. Fs plus ML phi dot squared sine phi. And then the second equation, ML cosine phi and ML squared. And then those two cancelled out, remember? And then this one is remaining, M phi minus MGL sine phi. Yeah, I'm happy when I see this. Why am I happy? It's symmetric. Yeah, I expect it to be symmetric, and it is symmetric. Moreover, I see terms which I recognize, like mass times acceleration, and here mass moment of inertia, ml squared times angular acceleration. Then there is a coupling. The point I made is that the transformed mass matrix on generalized coordinates is dense and is configuration dependent. So it's a function of the phi. Could also be s, but in this case not. And then on the right hand side I recognize the applied forces, but also these what we call convective terms. M omega squared r and those kind of things. Well, this is of course just gravity loading. When do I see you again? Next week? Yeah? It's the last lecture then, huh? Yeah. Yeah, there is one scheduled in an orange week, but we're not going to do that. Look at the schedule. Next week is the last lecture for quarter 3. Yep.